So welcome to part 2 of this. So we will be doing an engineering problem looking at groundwater pumping and solving for the drawdown, which is drop in the potentiometric surface. For example, if you have an unconfined aquifer giving like pumping. Okay, and the solution for this is called like the thesis solution, and we use a well function for this. So we will look at like a well function. Okay, so here this is like our problem is something like this. So here that would be my original potentiometric surface. This is like an unconfined aquifer. Here we have two confining layer, and now I have a well here which is like fully penetrating from the top of like my aquifer to the bottom of my aquifer, and then I started pumping. And when I start pumping, then you see this cone of depression. Like my potentiometric surface here will start to have like this conical shape. And the difference between my original potentiometric surface and the one after pumping, like that's like H node, so if that's like H node and that's like H here, that's like called the drawdown, like the drop in the potentiometric surface. So in this problem, like a community is installing a new well in regionally confined aquifer with the transmissivity of, so this transmissivity tell you how the aquifer is able, the ability of the aquifer to transmit water, and storativity of this number, so that tell you something about the storage. The planned pumping rate is 500 meter cube per day. There are several nearby well tapping the same aquifer, and the project manager need to know if the new well will cause significant interference with these well. So the theoretical drawdown, like here, this is drawdown, so the theoretical drawdown, like we give it as S, can be calculated using this function. So the drawdown, like this distance here from the original potentiometric surface to the drop in this potentiometric surface can be calculated as Q. That's like my pumping rate over 4 pi t, my transmissivity, and this well function WU. So what is this well function? So this well function, it looks something like this. It's a function of U. And what is U? U is like R squared. So R is the distance from the center of this pumping well. So like this distance here, this distance here, this distance here, this distance here. So here we want to evaluate the drawdown, like Z here, like the S here for a different distance, like 50 meter, 100 meter, like 50 meter, 100 meter, 500 meter, 5,000 meter, like 5 kilometers, so at different distances. So it's a function like this. U is a function of R, S, like this, storativity, T, the transmissivity, and the time, like for how long I'm pumping, like for how long I've been pumping. Okay, so basically, that's the first thing I'm asking you. Write down user-defined, like write down this well function, and you see this well function here also has this factorial. So this is like factorial of 2, that's 2, factorial of 3, that's like 6, factorial of 4, that's like what, 24, right? That's like 4 times 3 times 2, yes, and so on. Okay, so, and you can stop, like you can stop here at this term. I mean, if you want to continue, you can continue, but like stopping at this term should be fine. So I already did this for you, so you don't have to type it. So let's look here at, so I called it like WU, the well function. So this well function here, basically it's a function of U, and U needs like 4 input. It needs R, it needs S, it needs T, and it needs like the time. So here is a well function. It will take the R, it will take the storativity, it will take the transmissivity, it will take the time. We'll pass them to U, and then we will pass U to WU, and then this function will give us like WU value. So we already defined this for you, so you can directly use it. So let's write our input first. So like our input like t is equal to 150. S is equal to 0.0005. Okay. What other inputs do I have? Q is equal to 500. Okay, so these are like my inputs here. Now write down the write and use the user-defined W function. So now I have already written it. Now I just need to use it, so I can say like my WU value, that would be equal my WU function, and then I pass to it like see here it already tell me it takes R, it take S, take T. So I want to evaluate this for different distances, which is R here is giving. So let's just, I can copy this one. So Control C. So that's like my R. So that's like a vector here. So, and then I just like run and see what I'm getting. Do you mean... Okay, because I don't have t defined here, like this. Do you mean like this big T? No, I mean like small t, and then I need to define like my small t here, which is okay for the new well after 30 days. So I need to define my small t here as like 30 days. So now I should do something like this. So I got something that looks like this. Okay. Now it tell me, so now I have my W, now it tell me calculate the drawdown. So remember the drawdown, that's this equation. So my drawdown like S is equal to Q times this WU, which is I calculated it here. So this WU is a vector, remember, because I'm calculating it for all the R. So like if you are doing this by calculators, that would be killing, or if you are doing this with Excel, that would be like not like as easy as you're doing it here. So that's like time 2 time by time t. So now that should be also like a vector, okay, for each R. Okay, so if I run this, then I got like my drawdown. And then it's telling you present your results distance in kilometer. So here, and like drawdown in centimeter, for example. So let's make like a table. And in this table, so that's like in meter here. These distance here like are in meter. Let me hide all these guys here. Let me hide all these guys here. Let me hide all these guys here. And then I want to like present this guy in kilometers. So basically I divide, so I say like R divided by 1000. And then in make a new like line and then present this in centimeters. So this is already given in meter. To present it in centimeters, and I multiply by 100, for example. Okay, and then let me transpose this so that it would look nice. So I got something that looks like this. Let's look at my, maybe see it here, like the tables that I have here. So I have a table that looks like this. I got like these numbers here. Did I do any mistake here? I mean, let's see what mistake did I do here. I mean, I didn't get these numbers when I did this before. Maybe did I put any numbers? So here's just like 150. Maybe like 1, 2, 3 zeros, like 1, 2, 3 zeros. That's like 500. That is T. See, time here is like 30 days, but anyway, so that seems to be correct. Maybe. So here, like the drawdown, I have like 5 meter at a distance of like 50 meter, and I have about 20 centimeter at a distance of like 5 kilometers. That's like the drawdown. Okay, and now it tell me is like. Let me run this, see if I get what am I getting here. So here I'm getting a different values. which I wonder why. Okay, so maybe, oh, okay, see, I think I make a mistake here. That's a mistake. That should be 4 pi, not 2 pi. Okay, so that's the mistakes that I did here. Okay, now, that's what I got before when I solved this problem. So I got here like at 5 kilometer, I have like 10 centimeter drawdown. At 50 meter, I have like about 2.4 meter drawdown. Okay. Now, what this is telling me, again, like another thing is like plot your results with a distance of r in meter and add and draw down in meter. So now it's telling me use plot, draw down. We will learn. So we still didn't do plotting. We will learn plotting in the next lesson, but this is just to prepare you for the next lesson. So basically, it will be plot. I just want to plot my R and like my here like drawdown. Let me call here this as like drawdown. Okay, call this like drawdown so that I will be consistent. I will call this like drawdown here. Okay, so that would be like drawdown, and it's telling me here basically like this means like this dash means like a solid line, and I want my data point like at each of these data point to be like to show a square. So let me show you how this would look like. So if I plotted this, then I got here like at each, like at 50 centimeter, I have like this is square here, and then I have at 100 centimeter, at 100 meter, 50 meter, 100 meter, 200 meter, 300 meter, 400 meter, 500 meter, and this is so on. Like the last one would be the 5,000. So like if I put like a circle, for example, then that would be like a circle. If I put like an X here, that would be like an X, okay? So, but I'm telling you to square, that's like an S. So that will give you like this square here. Okay, now here I'm telling you another things to do, like to improve visualization, reverse the y-axis to get drawdown similar to the figure. Like you see here, drawdown, when you are close to the well, you have more drawdown. When you are far away from the well, you have less drawdown. Here is it's like flipped upward. Like so, here I just like want to improve the visualization by reversing the y-axis. So, how to do this? So to reverse the y-axis, use this function. Okay. And we will learn this next lesson. So like to reverse the y-axis. So basically, what does this say? I'm getting get the current axis handle, and then y direction, and then reverse. So now I got something that at like a distance of 50 centimeters, that's where I have my maximum drawdown, and as far as I go from the well, I get less drawdown, similar to the figures that we got here. Okay, so that's all for this exercise. So now you know the well function, and you know how to use this well function to estimate like drawdown at different distance from your pumping well. Okay, that's all for this lesson, and see you in next lesson where we will be learning about plotting in MATLAB. And you will learn how to do something like this, like reverse your x-axis, your y-axis, your x-axis, and many more other things. Okay, that's all, and see you like next lesson. Bye bye.